Hey, good morning, everyone. I'm happy to be here, and my name is Kai Wan. I work with Dr. Shashank Priya, majorly in charge of the solar group in the EL building. So today I'm going to introduce Luyao, who is a postdoc here in our group and doing great jobs in solar cell and thermoelectric. And basically, he's a material scientist, majorly developing new materials that could bring new opportunities to both fields. And maybe you can start, Luyao, and I cannot wait to see a great presentation.
Okay, so good morning, everyone. So I'm Luyao. It's a great honor to have an opportunity to present some recent result about my projects.
Excuse me, Luyao, you're not in the presentation mode.
Okay, so let me show.
Yep.
It's working.
Yep.
Okay, and today I will talk about some data or like results about this topic. So molecular performance of the F4-TCNQ doped tin-based perovskite. So basically, this field is kind of new because for when we talk about the Halide perovskite, we all like thinking about to make it to solar cells because it has very good electrical optical electrical properties to obtain like very high efficiency for solar cells. But recently we found that this material also has very low thermal conductivity. This is a good feature for like developing its thermoelectric properties and even to make a TE module from this material. And but there are still some like things need to be solved, like for example, not very good electrical conductivity, and also the lack of measurement system for get thermal conductivity from the SThM sample. So for this work, we we mostly focus on these two aspects. First, try to like improve the material property by some like doping method, and another thing is try to establish some new method to measure the thermal conductivity of the SThM samples. So let's get started with my presentation. And here's my outline. I will first start with some introduction about the thermoelectrics and also the highlight perovskite material we are focusing on. And then we'll talk about the materials and also the method we used to boost the electrical conductivity and also the new measurement setup for getting the thermal conductivity of the SThM sample. And finally is summary and outlooks. So let's start with the introduction part. So the thermoelectric material is able to convert the heat to electricity based on the Seebeck effect or called the Penn effect. So when we apply some temperature difference onto the semiconducting material, so the majority charge carrier will diffuse from the hot side to the cold side, and will like induce some electric field inside the material, as shown here. So for different type of the semiconductor, the building electrical field is in a different direction. And if we kind of coupled this P or N type material together to make this kind of single module, we can generate some electrical flow by applying the temperature difference on the bottom and the top. And also in the other way, if we apply some current onto this module, it will generate some temperature difference from these two sides. So probably can get some cooler or like a heater from this setup. And basically the current flow generated or like we applied is a DC current. this is good to like incorporate with some advanced electrical device. For example, solar cell. Solar cell will produce a DC current, and we can directly use this current to make to run the TE cooler. And also we can like use DC current generated by the TE module to turn on the LED light. This is also DC current, so it's has a great opportunities for this device based on this thermoelectric effect. And another thing why we are interested in developing this kind of materials is there are a lot of heat waste energy in the world. So as we can see, like, so there are a lot of methods to generate like energy, like thermal power, nuclear power, or like other things. And also there are some like we drive a lot. There are a lot of vehicles, and but the efficiency of like utilize energy is quite low, as we can see here. Almost 66% of energy is lost, like in terms, for example, in terms of waste heat. So if we can utilize this thermoelectric device to efficiently like harvesting this kind of heat, waste heat, this will be great potential like for the use of the energy we on hand. And also there are some quite fancy applications. Let's, for example, we can make some flexible module, TE module. We can use the body heat to generate some electricity to power up our, like, for example, the watch or even cell phone. This is great. And also, as I mentioned, we can make some cooler from these materials. So there are some mini refrigerator available right now. So, but for this refrigerator, it's different from the traditional one. There's no like moving parts or vibration parts inside of the device, indicating like it's kind of like noise free and it's very easy to set up. Just need a TE module and like just need some DC current. Then you can generate some like you can generate some refrigerator and get some cooler temperature from one side. And for the state-of-art TE materials I shown here, there are a lot of types, and the figure measure of the material is ZT value. So basically, we want to get a ZT value over 1. So probably that's a requirement to give a reasonable efficiency of like convert heat to electricity. And currently we researchers work on like dismantle this kind of material. And also there are some semiconductor polymer, this is PSS. So the reasons why they are working on this material is that they can be flexible first, and also it's easy to fabricate. They can be like solution processed, and plus the thermal conductivity of this material kind of low comparing to the traditional TE materials. This is good to generate a high ZT value. But there are also some problems need to be addressed for this polymer, for semiconductor polymer. And also, as I mentioned, we need a high electric conductivity and also low thermal conductivity, as the ZT equation shown here. So we relate to these two parameters. We want a higher electric conductivity. Probably can use some dopants to modify, to optimize the materials. And also we can try to use some method to enlarge the crystal size to give us like higher mobility of the materials. And on the other hand, for the thermal conductivity, usually it can be divided into two parts. First is electronic thermal conductivity. It's directly related to the electrical conductivity, as the equation shows here. It's kind of straightforward, But for the other part, the lattice part, it's kind of complicated. It's phonons traveling through the lattice to transfer the heat through the material. So as shown here, it's kind of vibration, transfer of the vibration. So how strong the bonding is and how long is mean free path for the phonons inside the material. And also if there are some impurities inside or like some phase separation regions, they will generate some scattering center. So all these are affect the lattice conductivity. But overall, so it's sum of these two parts. If we want to get a lower thermal conductivity, so we probably do not to touch the electronic part, because we try to reduce the electronic part, it also sacrifices the electrical conductivity. That means we can kind of reduce the ZT value overall. So researchers are mostly work on like try to get a low lattice thermal conductivity of the material. There are a lot of approaches, but people are always looking for new materials because the lattice is kind of intrinsic quality parameters for the materials. So people are always looking for some electron crystal and phonon glass materials, which can give us high electrical conductivity and low thermal conductivity. And I have been working on like perovskite, highlighted perovskite for almost 5 years. So we all know that this material has very good optical electrical properties. And there are some features we are looking for to explore its thermoelectric applications. Let's see, we have this very good electrical transport properties inside this highlighted perovskite. So this material basically is it's kind of like ABX3 structure. We have, as let's shown here, we have methyl-ammonium here, and metal usually it's lead or tin, and also halide on this side. So, and recently, people found that this structure is kind of unique to have a phonon scattering inside the material, and resulting very low lattice thermal conductivity. So this is these two features pretty good for like high performance thermoelectric materials. But for this ladder-based perovskite, they found this the electrical conductivity of the intrinsic ladder perovskite is very low. It's like 10 to the minus 3 or 10 to the minus 4 Siemens per centimeter. This is not good for thermoelectric material to convert some to like apply some current, although it probably has a very good thermal voltage, but the current will be really low and resulting in a very poor power output. So people are now we are like looking for some perovskite, like tin-based perovskite, because this tin atom will contribute more to the valence band because of the s orbitals. It will give us even better like electrical conductivity. This is good for comparing to the ladder-based. And also the di11 tin is easy to be oxidized to the tetravalent, inducing some self-doping. So as shown here, this is a SThM tin highlighted perovskite. So the electric conductivity is relatively higher than the lead-based perovskite, as I mentioned. So for the lead, it's only about 10 to the minus 3. So here we can get like almost over 100. And when we put this material in the air, there are oxygens. So for a certain time, it will be kind of oxidized and inducing some self-doping, resulting in increase of the electrical conductivity. And also, although on this side is the cesium rather than the organic cation, the organic cation has more freedom to for the motion and probably will leading to more photon scattering effect. But the cesium is here, it still has certain freedom to motion inside of the cage. So they still can give us kind of scattering of photons, lead to a low lattice thermal conductivity. And comparing with other typical T material shown here is pretty low. This is good for obtain ZT value, good ZT value. But up to now, the record ZT value is about like 0.15 based on this material. It's not that good as the state-of-art T material, but it has huge potentials and huge rooms to improve. So we can try to induce some dopants or like do some nanostructured processing of the material, and we probably in the future we can boost the ZT value even to like over 1 or even higher than the typical or the traditional T materials. And people are now very interested in this field because this is a new field. It's kind of start to blowing because the material perovskite, Halide perovskite, quite popular for the solar cell device and has a very good, unique features. So there is a lot of opportunities to get very good material from these crystal structures. So, and then I will talk about our work on the F4-TCNQ doped tin-based perovskite. So basically, we want to get a higher electroconductivity and try to maintain low thermal conductivity. So we pick up this F18 iodide. So it's tin-based, probably have an intrinsic, kind of high intrinsic thermoelectric electrical conductivity. And we have this Fa cation on this side. It's kind of like have more freedom compared to the cesium because it's have a degree for like rotate or like twist. Probably even better than the cesium will give us even lower thermal conductivity. And rather than dope inside of the lattice, try to replace this atom in the lattice, here we try to use some small molecules to dope the material in the molecular level. So because this F4-TCNQ has a low-lying low energy, so when it mixed with or like doped into the Fa tin iodide, so the electron, because the Fermi level of the Fa tin iodide is around here, so electron will transfer to the F4-TCNQ. That way, we can induce more holes inside of the Fa tin iodide, leading to a p-type doping. This is a way to improve the electrical conductivity. So first, we want to confirm this doping method is really happen inside the perovskite material. So we use the XPS to check the fluoride, nitrogen, tin, and as well as the iodide to see if there are any like peak shifts, the binding energy shifts or not. So first we check the fluoride. We can clearly see there are some peaks of the fluoride in the doped sample, indicating the material is really inside. And then we found that there are like very large band energy shifts, indicating the chemical environment of these elements are changed after inducing the F4-TCNQ. That indicates the F4-TCNQ really doubled into the perovskite and make some changes. And then we measure the electric conductivity. We can see only like add a little bit F4-TCNQ, we can dramatically boost the electric conductivity, like over like So almost over three times compared to the pre-SThM. And the electric conductivity, the increasing and decreasing is consistent with the mobility and charge carrier concentration we measured. But for the higher doping level, the higher concentration of F4-TCNQ, so there is some like dramatically reduced drop, rapid drop of the electric conductivity. This is probably due to the excess of the F4-TCNQ inside of the material. So there will be some cracks and some phase separation of the thin film we can see from the SThM. So we want to maintain the dopant level around the concentration of F4-TCNQ around 0.05 milligram per milliliter. This is optimized concentration we will use. And after addressing the electrical conductivity sides, we improve the electric conductivity. Then we will try to measure the thermal conductivity of this thin film. But at this time, it's kind of difficult to measure the thermal conductivity directly from the thin film. There are some methods available, but it's kind of harder to set up. So here we develop a new method for measuring the thermal conductivity of the thin film. It's called scanning thermal microscope. So basically, it's AFM setup and coupled with some design circuit with some thermal parts, like as shown here. So this model based on the thermal contact resistance. So when the tape is attached to the sample, there are two ways to transfer the heat between the tape and the sample, because it's the tip is the radius of tape is very small. So the micro content cannot be ignored in this case. So here we try to set up this model and use these equations to address both micro contact resistance and also the micro contact resistance, because based on these two equations. So this is related to the thermal spreading, and this is more related to the surface conditions of the thin film. So there are a lot of parameters involved, but we can address all these parameters from the AFM mapping. And here shows the equations. So we get the total thermal contact resistance by this equation 3, sum of these two parts. And then we can set up a circuit to measure this thermal contact resistance. And we use this setup, and we use some fixed thermal resistors, and we apply some voltage and maintain some temperature difference between the tape and the sample. And we can address this equation. The total energy is equal to the tape surface, equal to the fixed resistors, the energy heat generation of the fixed resistors, and also the temperature difference between the sample and the tape. And we can address this our system through this equation, the sum of the contact resistance and also the resistance of the sample. And then we can kind of correlate the current with all the parameters we shown here. So basically, the current we can get is depends on the temperature difference we set, the voltage we applied, and the fixed resistor, and also the lot of micro parameters, and as well as thermal conductivity. These two parts we can fix during the measurement for the system, and all these parameters we can measure from the AFM mapping. The only thing we are unknown thing is like the thermal conductivity. So then we can relate the probe current with the thermal conductivity shown here, the equation shown here. So because these two parts we can fix, so it will be a system constant, and all the other parameters we can measure from the AFM mapping. And then we found that these two parameters is shown here. And first we try to validate the setup to measure some well-known perovskite materials. Let's see the typical MA lead iodide. So the value we got is about like 0.5. This is consistent with some literature reports, so indicating our mode is suitable for perovskite material. And we try to rewrote this equation into this figure version. Then we can directly obtain the thermal conductivity by measuring the probe current during the mapping. And here's the result. So here is the first 5 figures is are the F mapping images of the thin film, while this later 5 is the current mapping during the AFM measurement. And we can obtain all the parameters from the measurement. And for different concentration of doping, we can get a different average probe current from this mapping. And overall, we can calculate the thermal conductivity depending on the equation we show here, equation 9. And we found that this Fa-tin iodide exhibits even lower thermal conductivity comparing to some like lead-based or like cesium-tin iodide as shown here. It's only about like 0.2. This is a pretty good value for tin materials. And also, this is the first report on the experiment data for this F18 iodide thin films. So after that, we try to measure the Seebeck coefficient of the thin film doped or like intrinsic thin films, and we calculate the ZT value. So we can obtain like 0.19 the ZT value from this doped thin film at room temperature. This is pretty good compared to the previous literature reports. Some only about 0.15 at like 300 Celsius degree. So we can achieve even higher ZT value at room temperature. So this material has more potentials to make a module. And also because it is a thin film, we can even make a flexible tin module based on these materials. And finally is a summary and outlooks. So in this work, we try to improve the electric conductivity by some small molecules doping as shown here. So we use this F4-TCNQ to induce p-type dope into the perovskite and give us increased electric conductivity. And also we try to set up a new method system to measure the thermal conductivity thin film based on this SThM method. And we can obtain pretty good ZT value from this material at room temperature. And because perovskite, we know it has 3 sides, ABX. So we can try to like change the different elements on these 3 sides to obtain new material and to see what we can get from the thermoelectric performance. And also we can try to mix the cations. We have like these 3 mixed cations inside of the perovskite. So the phonon scattering will become like even more like it can scatter different wavelengths of phonons and will induce like even lower lattice thermal conductivity. And also we are trying to probably can try to use other last structure of the perovskite, let's see the vacancy order perovskite. Basically, we remove the B-side metal from the typical 3D like perovskite, so we'll generate more rooms for space for the cation to move and rotate. Probably can get even lower thermal conductivity. And also we know that the perovskite usually has a very good optical electrical effect. It is like used, they are well used in like solar cells. So for some tin-based, it can absorb light, and also it can convert heat into electricity. We can make a multifunctional energy generator in one device. This is pretty good. And also for the thin films, we can try to make and design the flexible tin modules. We can wear on our hands to like power our watch, use our body heat. So these are all the outlooks. Probably in the recent future, we can obtain all these, we can address all these fancy applications. And that's all. Thank you for your attention. I'll take any questions and comments.
Thank you, Luyao. This is really great and very informative. So there might be some questions from the audience. Any questions?
Hey, Luyao, this is Beth. I wanted to ask one question. So this material, because of the temperature limitation, probably most of the application would be closer to room temperature.
Yes.
And so far, room temperature GT is very low. When you go to high temperature, it keeps increasing, which is good. But what are the strategies you could apply to bring this peak GT closer to room temperature in this material system? Any idea?
Yeah, this is a good question. So for this work, so because we didn't investigate the parameter or like the ZT value at high temperature, we just measure at room temperature. So we try to increase the electric conductivity by some dopant, and finally we boost the ZT value. So probably you can try the similar way to use other dopant, like suitable dopants, or like replace some elements inside of the perovskite. Try to boost the electric conductivity while remaining very low thermal conductivity. We can get a high ZT overall ZT values. But for high temperature, like if you want to use a perovskite at high temperature, probably we needed to switch the organic cation to some inorganic cation, like let's see the SThM or like other options, because as far as I know, the all inorganic perovskite has a better stability at high temperature. Probably they will produce like higher ZT value at that temperature. Probably you can use that material as candidates.
Yeah. Can I ask one more question? So how does this compare with some organic or polymer based thermoelectric? What are the advantages of going to perovskite or going to organic based thermoelectric material? I think there are some reports of it. Yeah.
So let me go back to the very first. So here we can see there are one data points of the PSN. This is a semiconducting polymer. So compare with the organic material, so the advantage of this perovskite is it's like a low cost low cost processing. So for organic, like semiconducting material, let's see for the P.PSS, it's kind of expensive. If you want to make a like a bar sample to make some T module, it's very expensive. And you know the material usually used for like in organic solar cells, let's see, P3HT or PDB7. It's very expensive. So it's only like for the research users rather than the manufacturing. For I mean for the T application. So for perovskite, it's quite cheap. I mean the processing and also the raw material is abundant and its price is quite low comparing to the. I think it's kind of an advantage. And also for organic material, the stability is also the problem, because you want to get a higher electric conductivity, you need a kind of like highly doped material. Let's see for this P.PSS. So it's the pH value is very low for this material. It's almost acid. So you do not to like want to put any metal contacts onto this material for like a real T module, right?
Yeah. Okay. Yeah. Thank you, Luyao. This was a great presentation.
Okay. Any other more questions? Maybe I can ask while other people are thinking. So yeah, I work on the solar cell field, and I learned that this type of Halide perovskite material can be used in solar cell, but mostly the solar field is dominated by the silicon materials. So, but for Halide perovskite, there could be a flexible solar cell. Then that will open a new niche market for this new material. So I'm just wondering if this same play can be used in the thermoelectric. Then, for example, you can develop some new flexible and maybe fabric or something like that products to be involved in this market.
Yeah, that's a good question. This is good suggestions. I mean, like because we made thin films from this material, so we can definitely make a flexible module. We just need some like flexible substrate and design of the P-like or N-like to make it like thin film shape. So it's not difficult to like realize a flexible module.
Right.
Yeah, because you already have the thin film and we have the materials, and we just need to like choose some suitable PN type materials and combine them together to make a real module. And also the device design is quite important. Because we cannot use this traditional two legs containing with each other. We cannot use it because the thin film, we cannot make this kind of shape. We probably need to redesign the module, single module, and kind of like assemble it together, like onto the flexible substrate. And even we can like combine this flexible T module with the solar cells, because we know the solar cells usually can only like absorb the visible light, while the infrared light usually will convert to heat. We can use this T module to absorb the heat from the infrared, so the overall efficiency of the device will be improved significantly. Probably will kind of like defeat the silicon solar cells. I mean,
yeah, I think this innovation in the device structure is very important. And as far as I know, there are some people working on the solar cell. They develop some fiber like devices. So by combining those fiber and weaving them into a cloth, then they can put those like solar cell on their like clothes. So actually this kind of innovation is really important. And I think shifting from solar to this thermoelectric using similar ideas might be some research directions potentially.
Yes, great idea.
Okay. I think there's no more questions from the audience, right? Okay, so maybe we can stop here. Yeah, thank you, Luyao, for this.
Thank you.
Yep.
Thank you.
Mhm.